Welcome to the MH2801 video segment on orthogonality of sine 2 pi nt over t. Now consider the integral from 0 to t of a product of two sines, the first one being sine 2 pi mt over capital T, which is a period, and sine 2 pi nt over capital T dt. Now, in order to evaluate this integral, we need to convert the product of two sines into the sum of two trigonometric functions. And the identity that we will use is a multiple angle formula, but not of sines, but of cosines. So we will write those down. Cosine A plus B is equals to cosine A cosine B minus sine A sine B, and of course also cosine A minus B is cosine A cosine B plus sine A sine B. So if we take the difference between these two cosines, we will find that cosine A minus B minus cosine A plus B will be equals to 2 sine A sine B. Now here we will identify with A 2 pi mt over t, and with B as 2 pi nt over capital T, so that A minus B will be 2 pi m minus nt over capital T, and A plus B is 2 pi m plus n t over capital T. Now, let us make use of this result to evaluate the integral. We find that the integral from 0 to t will become 1/2. Okay, let's put a square bracket around the integrand. 1/2 cosine 2 pi m minus n t over capital T minus 1/2 cosine 2 pi m plus n t over capital T and then dt. So both of these are simple trigonometric functions. It's a simple cosine. So when we integrate it, we will get a sine. So what will we get? We will get sine of 2 pi m minus n t over capital T divided by 2 pi m minus n divided by capital T, and here we will get sine 2 pi m plus n t divided by capital T, and again divided by 2 pi m plus n divided by capital T, to be evaluated at t and 0. Now what happens when we evaluate this integral at the upper limit t? Now if we substitute t into little t, we will find that in the first term we will get sine of an integer multiple of 2 pi if m, provided m is not equals to n. So this sine of an integer multiple of 2 pi is of course 0, and the same thing happens if we substitute it into little t in the second sine. It will be sine 2 pi m plus n, which is of course an integer multiple of 2 pi. So this sine is also 0. And what happens when we substitute the lower limit into the variable t? Now in the first sine, we will get sine of 0, which is naturally 0. And we substitute into the second sine, it's also sine of 0. So both the upper limit and the lower limit gives 0, and therefore the whole integral itself is 0. Now what if, okay, so this is for m not equals to n. Now what if m is equals to n? Now if m is equals to n, then what the integral that we will be evaluating is the integral from 0 to t of sine square 2 pi nt over capital T dt. Now here again we need to make use of some double angle formula, and the double angle formula that we will make use of is actually that of cosine 2a. So let's write down cosine 2a, Now this is cosine square A minus sine square A. Now we have a sine square in the integral. We have a cosine square and a sine square. So we just want to keep sine square in this expression in terms of cosine 2A. So what we do is we make use of the trigonometric identity, cosine square plus sine square equals to 1, to write cosine square as 1 minus sine square A. Okay, this second minus sine square A was originally from cosine 2A. So this is 1 minus 2 sine square A. Now if we make sine square A the subject, we will find that this is 1/2 of 1 minus cos 2A. So let's substitute that, okay, here, and of course here we are going to identify with A 2 pi nt over capital T. So let us continue with evaluating the integral using this double angle formula. We will get integral of 0 to t of 1/2 1 minus cosine. Okay, A is 2 pi nt over t, so 2A it will be 4 pi nt over t dt. So if we evaluate 1/2 from 0 to t, we get t over 2. If we integrate cosine 4 pi nt over capital T from 0 to t, we will get minus 1/2. Okay, we get here sine 4 pi nt over capital T divided by 4 pi n, no t, divided by capital T. So I need to erase this. Oh, this is a big eraser. So small one will do. Okay. And then evaluated at t and 0. So again, we see that if we substitute the upper limit into little t, this becomes sine 4 pi n, which is of definitely a integer multiple of 2 pi, and therefore the upper limit is 0. And if we substitute the lower limit 0 into the sign, it will become the sine of 0, which is again also 0. So this second part of the integral, which comes from cosine 4 pi nt over capital T, evaluates to 0, leaving only t over 2. Now we can combine the two results together and write this as the integral from 0 to t of sine 2 pi mt over capital T, and then sine 2 pi nt over capital T dt is equals to t over 2 delta mn, where delta mn is of course the Kronecker delta, which you have seen earlier on. Okay, and this is equals to 1 if m is equals to n and 0 otherwise. Okay, and this relation here is called the orthogonality relation of the signs. That is to say that sine 2 pi nt over t capital T and sine 2 pi nt over capital T, these two functions are orthogonal to each other over the time interval 0 to t, but they're not normalized, because if we integrate sine square of 2 pi nt over t, we don't get 1, but we get t over 2. But for evaluating Fourier coefficients, just having a orthogonality relation is enough. We do not actually require the functions themselves to also be normalized. Okay, so in the next video segment, we will talk about the orthogonality relation between sines and cosines.